I'm really very happy and very honored to be here to present this research on binary analysis for vulnerability detection. And I have also acknowledged the research projects which has funded this research, partly for DSO National Labs and also with the National Research Foundation. So I'm coming from Singapore. Many of you would be familiar with Singapore. Singapore is a small country, about 12 hours plus flight from Luxembourg, and has about 5 million plus population. Specifically, I'm from the National University of Singapore, which in 2005-2006 we celebrated our centenary. So it was established in 1905, and it has a large graduate and undergraduate student population from a large number of countries. So what I will be talking of today is this is a project under this cybersecurity research program from the National Research Foundation in Singapore. The cybersecurity research program is a 5-year program where a certain amount of funding has been set aside to support research as well as infrastructural efforts in cybersecurity. And specifically, strategically, these 6 themes have been identified. And under that, I will be talking about one of the projects under this program. Okay. So the focus of the project that I will be talking about is on COTS integrated platforms, where we take the view that systems really cannot be provably secure, and we really have to build up systems from COTS components, commercial off-the-shelf components. So what kind of semantic analysis or system-based approaches that you can envision so that even while assembling a system from commercial off-the-shelf components, you would still be delivering a trustworthy system. So this has a large number of approaches, so I will not be talking about all of these approaches today. I will focus more on the testing and analysis aspects, the security testing and analysis aspects, where you do not have maybe the source code of the program, or at least you don't have the full source code of the program, and how you can analyze the program binaries for finding out and possibly fixing vulnerabilities. There are also other aspects to this project that was also mentioned by Lionel in his introduction. There is work on system hardening, making it more resilient against attackers, system level verification, as well as some very nice work on data protection that we are doing, and I will not be talking about all of those. The overall view of the project is really this 4-fold approach, where I will be talking more of the vulnerability discovery. And there is collaboration with the government agencies, in particular the Defense Science and Technology Agency, as well as number of industrial collaborations in this project. The use of the research, before I begin talking about the specific techniques, the use of the research is, these are some sample uses of the research, where it could be useful to the agencies for procuring software, because you can run these kinds of analysis against the binaries on the evaluation version prior to the procurement, as well as also it could be useful to the agencies on the procured software. So this is the overall usage. At this point of time, before moving on to the research, I'll just play maybe one video on the vulnerability detection.
This is Bob. Bob receives an email with an attachment. This attachment is a document which Bob can open with a PDF reader program. Once he opens the document, he finds that his credit card details have been stolen. Now, because of a vulnerability in the program that Bob uses to open the file, his computer gets compromised. As security researchers, we analyze such programs to understand whether they can be used to compromise a computer. This is called automated vulnerability detection. We can distinguish 2 main techniques. Our tool Hercules is a very effective whitebox fuzzer. Here we demonstrate how it crashes Acrobat Reader. Our tool EFL Fuzz is a very efficient blackbox fuzzer. In this fast forward, we demonstrate how it finds the first vulnerability in under 10 minutes. Our tools expose vulnerabilities in large, well-known programs that take complex files as inputs. And the best part is, it works directly in the program binary. Our fuzzers are both more efficient and more effective than state-of-the-art. Our tools have been used to find several severe vulnerabilities in widespread programs. Fortunately, these vulnerabilities have all been patched by now.
So, the application of these techniques is best embodied in the recently concluded DARPA Cyber Grand Challenge finals. So, this was an effort from DARPA which you might be aware of, where they tried to hold a CTF, a capture the flag kind of competition, where there would be no human trying to protect the system, trying to protect a network, but the computers, specifically program analysis systems, will be trying to protect a set of hosts. So, some of the research that I will be talking about have also been applied in the context of this DARPA Cyber Grand Challenge. So, hopefully this provides a nice motivation for the research, and let me now move into the techniques. So, the technique that I will be talking about is specifically fuzz testing. It was pioneered by Barton Miller in 1988, so it's about 30 years old, and just in 2016 Microsoft has launched the Springfield project, which is actually providing fuzzing as a service, and Google also has this OSS Fuzz on open source, which you might be familiar with. So, I'll just present a real story. I was just preparing some lecture notes on fuzzing. This is the actual date on May 4th, because I was trying to teach this in my software security class. So, how best to start? So, at 11 a.m. I more or less finished deciding on the structure of the lecture notes and so on, and I was trying to think what would be a good example that I can give, and I don't want to keep on giving old examples. So, I only had to wait for 11 minutes, and by 11:11 I actually had an email update of the latest case where fuzzing would help, an integer overflow in Boeing. This is really a classic method where sending out malformed inputs helps you detect the vulnerabilities ahead of time. So, I will not get into a fully formal definition of fuzz testing. Roughly speaking, this is a way of providing inputs to a program where you don't have any knowledge of the source code of the program, providing random inputs or semi-random inputs to a program with the goal of crashing the program. So, whenever we talk about testing, there is a notion of an oracle or expected behavior. Here, the oracle is very simple. You just want to produce inputs which crashes the program. Usually, the distinction is made between crashes and hangs. And as a result of this, fuzz testing can be automated to a large degree. So, this is the original definition of fuzzing, but of course, since then fuzzing has moved ahead quite a bit. So, I will distinguish between three kinds of fuzzing. One is the black box fuzzing, which is as embodied by commercial tools like Peach and Spike. So, here there is a seed input, and usually there is an input model provided in some format like maybe an XML format, and you just try to generate inputs by taking into account the input model and keeping on mutating them so that you can actually crash the program. Note that the model that is provided is on the input domain. There is no model provided about the program behavior. So, you really do not have any view of the program. It is still black box. There is only an input model that is being provided. The second suite of techniques, so these are all, we are just doing a very quick literature survey. The second suite of techniques goes under the name of graybox fuzzing. The gray box has been cut off from the top of the slide, as embodied by the AFL fuzzer. So, here there are seed inputs that are fed into the fuzzer, and they are of course mutated to produce new inputs, and then the fuzzer actually selects some of these mutated inputs and puts them back into the queue for the fuzzer to consider them again. So, how does it decide which of these mutated inputs to choose? It decides so based on an instrumentation of the program, and this is why it is gray box, it is not black box anymore. There is an instrumentation of the program to expose the control flow transitions being taken, but then you do not have view of the individual transitions being exercised, you only know whether a new path was exercised. So, the fuzzer will only tell you that okay, you managed to exercise 200 paths by running 1000 inputs, okay? Because of course, many inputs might go through the same path. So, this is why this is gray box. It also goes by the name of coverage based gray box fuzzing. The third one is whitebox fuzzing, which is really program analysis, and here the technique that is used is dynamic symbolic execution, and really you try to generate a random input. Probably it goes through this path in the form of the bold arrows, and you really try to capture the set of inputs which exercise the same path in the form of a constraint, typically a satisfiability modulo theory constraint, an SMT constraint, and then you will systematically negate small parts of the constraint to generate new constraints which then exercise more paths in the program. So the problem statement that we are looking into here is how to direct the exploration to reach certain locations or targets in a program binary or to enhance the coverage. These are very large scale program binaries. Typically we are working with things like the Adobe Acrobat PDF reader maybe. So that is the scale that we are talking of. Many of these programs are file processing programs, so they could take highly structured inputs, and you would be given inadequate test suite or seeds. So this is really the space that we are operating in, and now I will go into a little bit more details and talk of specific technical problems and what kind of achievements we have been able to make or not have been able to make. So the first problem that I will talk about is very, very simple. All of us in the room are surely familiar with this problem. Whenever an application crashes, like the Adobe Reader actually crashes, you would typically be given a choice, send error report and don't send. So I of course click the don't send, but a lot of us would click the send error report. And then these error reports go in, and there is a task of crash reproduction, because even when you send the error report, the exact settings, like suppose you were working on Adobe Reader and then it crashed, you will not be sharing with the developer the exact PDF file that caused it to crash, because that would probably give away some information at your end. So the developer does not have the exact environment or the exact input for reproducing the crash, and still she would have to reproduce the crash. So this is really the task of in-house debugging, fixing and crash reproduction. So this is the problem that we are talking of first today. So you are given a program binary, you are given some benign input files. I'll just read this out. This is the benign input files, and you would have some information about the crash instruction. So you have to generate an input which actually reaches that crash instruction. So technically this is only a reachability problem. You are given maybe like a Windows binary, and you would have to generate one input which reaches that specific instruction. Okay. So as you might imagine, this is of course a huge endeavor, so I will not get into all the details. I will just mention a few things that goes into the heart of binary analysis. The first thing is the control flow graph construction. Whenever we are doing source code analysis, program verification, we take for granted that the control flow graph will be available. In a program binary, even extracting the control flow graph is fair amount of effort, and the reason is there can be instructions where the jump target of the instruction is given by the value of a register, and the value of the register will only be known at runtime. So therefore you would not be able to tell at compile time what would be the jump target for those kind of register indirect jumps. So this is certainly one challenge. Another challenge that we have to overcome, so this is specifically for Windows binaries. In Windows binaries, as you know, there are modules, DLLs and so on. So we also have to construct the module dependence graph, where this is the definition of the dependence graph, where you have the executable modules as the vertices. So these are some of the basic challenges just to get the thing started. So this is the overall workflow of our analyzer. So the first step, as I mentioned, this is the very basic step, constructing the control flow graph and the module dependence graph. Subsequently, there is an exploration process. This is really the concolic exploration, concrete plus symbolic exploration, to explore this module dependence graph and the control flow graph inside the module dependence graph, so that you can generate one single input which reaches the module in question, and thereby we build up this hybrid symbolic file, because once you generate an input which reaches the crashing module, you can find out which bytes in the file actually are responsible, and then we have a more targeted concolic exploration. So all of this is fair amount of work. So I'll just show one key piece in this effort. So first, maybe suppose you have the hybrid symbolic file, so that you have an input which reaches the crashing module. So this is the target module, but just because you reaches the crashing module may not actually reach the crashing instruction and reproduce the crash. So then we have to explore inside this target module towards the crashing instruction. And then there is subsequently a backtracking. And note that the backtracking could go all the way, and this is really the very expensive phase of the search. And we really cannot afford to do a very unintelligent backtracking. So this is the key insight which actually allowed us to, there are many heuristics, as you might imagine, in this technique, but this is really the key heuristic which allowed us to run the experiments on programs that we use every day based on unsat cores. So suppose you manage to reach, somehow generate an input and manage to reach the crashing instruction, but you reach there without the crashing condition being satisfied. So since this is symbolic analysis, you are keeping into account the path condition, which is a logical formula capturing the set of inputs which go through the same path. So here the path condition says that BC1, so the branch 1 was taken in this direction, branch 3 was taken in this direction, and branch 4 was taken in this direction. So suppose this formula is unsatisfiable, that means there is something in the path condition that needs to be changed so that you reach the crashing instruction and you can actually crash. So we don't want to backtrack in an unintelligent fashion. What we did in this case is we tried to find out which portion of this formula is responsible for being unsatisfiable along with the crash condition. And for each of these portions of the formula or these primitive constraints, we are also maintaining a mapping in our analyzer which branch it maps to. So in this case, suppose the branch 1 contradicts the crash condition, then straight away the backtracking will go all the way to branch 1 and it will find out another path which probably comes back to the crash instruction and actually crashes. So this was the key heuristic. There were many other heuristics in this technique. On string processing, there were some heuristics. On managing loops, there were some, but I really don't want to get into all of these details. So as I mentioned, these experiments are pretty large scale. The time bound being set here is 24 hours. So we still want to find out the vulnerabilities in 24 hours. And the programs here, like this is the Windows Media Player, the Acrobat Reader, the Real Player, the Orbital Viewer, and so on. The comparison is, there are seed files being provided. Each of these are established CVEs provided in the CVE database. So we are not generating our vulnerabilities. So these are established vulnerabilities actually. And then the seed files are actually provided by a random search. So we just provide maybe 10 random PDF readers. So there is nothing hanky-panky going on with the seed files as well. The Peach is a commercial black box fuzzer, and S2E is a purely white box fuzzer. It's a purely symbolic analysis engine actually from EPFL. And we have built our Hercules engine on top of S2E, which is why we could, because S2E provides a lot of infrastructure and we are building it on top of it. Okay, so this is the first technique that I wanted to mention. We still, after doing this work, we still saw that there are a number of deficiencies. We are not able to handle many vulnerabilities in file processing programs. So just to give an idea about what is the scale of the problem here. So these are really the number of vulnerabilities. For 2016, I only have the data up till 31st of August or 30th of August, something like that. So I don't have the data for the last 4 months. So it's not that the number of vulnerabilities is necessarily reducing, but I don't have the complete data for the last data point. So these are the number of CVE assigned vulnerabilities. Of course, there could be many more. These are the number of CVE assigned vulnerabilities in file processing programs. So what we noticed is that we, for solving these file processing vulnerabilities and detecting them, we would need to combine the black box and the white box fuzzing. Just the symbolic analysis isn't enough. And this was really the key observation that, that allowed us to do that. The white box fuzzing is very good for finding out values for certain data fields, okay, because it's a constraint solving approach. So it's very good for finding out values for data fields. But if a certain data field is missing altogether, then the white box fuzzing clearly cannot find that out, and some search based approach is needed. So so this is the combination that we worked out in this approach. here we have the note that we are combining a black box fuzzer and the symbolic analysis based fuzzer. There is still the input model that comes with the black box fuzzer, and there is a test suite or a set of seed files which is quite inadequate. So, we have this file cracker which will kind of find out the different fragments or the chunks of these files and produce this pool of fragments, but then note that since this is inadequate, certain key chunks might be missing. So, and which is why the symbolic execution will get stuck. But when it gets stuck, we want the symbolic execution, the symbolic analysis to give us information about where it is getting stuck and why it is getting stuck, so that we can find out what chunks are missing and they can then be provided. So, I will just show this by this example. So, I do not know whether you can read this. Maybe I have another slide where this is blown up further. Maybe this one is easier to read. So, this is actually taken from the, I believe I took it from the libpng, which handles the PNG input files, PNG format files. So, here this is actually the tainted data coming in. So, this is tainted, and if you just follow the taint propagation, this is the potentially tainted data coming in, and then it is processed here, dereferenced here, it goes to chunk name, and then this is being used here. And it could very well be that this particular optional chunk, this optional data field is missing. This is a classic case where the symbolic analysis, the symbolic program analysis will get stuck. It will keep on backtracking to earlier and earlier and earlier branches without ever realizing that this data field is completely missing from the input. And this is not surprising. This is because it is doing a fully program analysis. It is not doing any input analysis. So, we need both the program analysis and also the search based input analysis to solve this kind of problems. So, what we will do in this case is, if we identify these kinds of if statements in the symbolic analysis, instead of doing any backtracking, we will find all these if statements which are actually always taking one direction, because if the data is missing, it would always take one direction and is impacted by this kind of taint chain. And then we will provide them, we will essentially provide these crucial if statements to this file stitcher, so that it can generate that data field, and then let symbolic execution find out the appropriate value of the data field. So, this way we are combining both the input analysis and the program analysis, and the results were arguably very pleasant. So, these are all very large scale programs. It includes all of the programs that I showed earlier. This is the Windows Media Player, this is the VLC program. I can give more details about each of these programs, I am happy to. And these are the input models. So, this is taking PNG files, this is taking the WAV audio files, the PDF files, and so on. And again, we are now comparing with Hercules, the earlier effort. We call the tool Hercules because this is a Herculean effort to solve the vulnerability detection. And now we call this maybe Hercules plus, and of course, we can see there are a number of cases where the purely symbolic analysis in Hercules was getting stuck for the reason that I mentioned earlier. Okay. So, now I will mention another effort based on graybox fuzzing. So, in each of these efforts for vulnerability detection, I am trying to give only the key insights. Each of these efforts were typically a couple of years of engineering and intuition before we could produce these results. Today I will talk about this coverage based graybox fuzzing now, which is actually an improvement of the AFL fuzzer that I mentioned earlier. So, just to recap, in coverage based graybox fuzzing, you have a test suite that goes through some mutators which produces mutated files, and then they are fed back, a selection of them are fed back into the input queue. So, just so that actually the algorithm that goes into a coverage based graybox fuzzer is not that complicated. So, just so that it is a purely search based algorithm. So, we can go through it and find out what are some of the deficiencies of this kind of fuzzing. This takes in some seed inputs and always generates these crashing inputs. So, it probably chooses from the seed, and then this is the key. Once it chooses a seed to mutate, it actually has this assign energy function, which tries to decide how much mutation, how much search it will do in this neighborhood. And as I mentioned, this is not black box, but this is gray box, and this is gray box because of this is interesting function, which essentially tries to see whether this is going through a different path than the earlier paths and tries to decide accordingly as best a decision as it can take. So now what we noticed is that for this kind of coverage based gray box fuzzing, it turns out often that it is going through the same path again and again and again, because it does not have an exact view of the control flow of the program. It is going through the same path again and again and again, and intuitively this is not very hard to see, because early on in the program you would have some checks which would rule out invalid file formats. If you are having a file processing program, early on in the program you would have some checks which would rule out invalid file formats, and these are the programs which would actually, these are the paths which would actually be exercised again and again. Suppose you had a valid PDF, you could mutate it and produce 2 valid PDFs and another invalid PDF, but then the valid PDFs that you produce, they again could be mutated to produce the same invalid PDF, and then you would actually go through this path again and again. So what we did in this approach, which was just published in this year's CCS conference, is that we view this as a Markov chain modeling. We find the probabilities so that fuzzing a test which exercises a path pi will lead to an input which exercise another path pi. So if we view this as a Markov chain, the only trouble is we do not have these probabilities, because remember, this is still working with program binaries. We do not have the control flow graph, we do not have actually the distribution of the inputs which are going through all the paths. So therefore we do not have all these probabilities. If we were to view this as a Markov chain, we want to prioritize the low probability paths. Specifically, if you look into this program, this crash me program, this would crash if you first get a B, then an A, then a D, then an exclamation mark. So really the probability of reaching here is very, very low, because first you would have to get a B, then an A, then a D, and so on. So really speaking, what can we do to estimate these probabilities even when we do not have the view of the control flow graph at all? So just to spice up the discussion here, so you could look into this graph. These are the actual results. This is the path indices computed by AFL. We are feeding, maybe in this case, the AFL and the AFL fast. So here AFL, you can see it's going through only 280 paths, even when this number of test cases have been fed. And in fact, half of them, this graph is on a log scale, half of these test cases are going through only 3 paths. So half of these test cases are going through only, probably even more than half here. And this is actually the graph that we have constructed from our modified AFL fuzzer, where it actually goes through a much larger number of paths with the same number of test cases. So what exactly is the secret sauce? So this is actually the only change we made. Earlier I showed you the algorithm which the fuzzer employs. This is the only change we made. So the AFL actually has this constant energy. So every time it chooses an input, it will say that, okay, you mutate this input to produce 500 mutations. Okay? So it has this constant energy. So pi is given this alpha I as a constant, whereas we actually gave a variable energy. Every time you choose an input which goes through a path which you have seen before, you try to modify the energy so that at a certain point of time, if you have gone through that path too many number of times, then you make that energy completely 0 and you decide not to explode that path again. So this is really the main change we made. And this actually made a lot of news beyond the usual usage and the impact. It also made a lot of news within actually 24 hours after which we posted the results and also made the tool available. It was also trending in Hacker News. And I'm very pleased to see this, this comment which somebody posted saying that this is a great example where academia shines and so on. So this is very pleasing to me, better than any award. And in this case, this particular technique, this modification of the AFL fuzzer, we also made it available to the CGC finalists. And one of the CGC finalists actually made an independent validation and found that this actually crashes 19 times faster as compared to AFL. So actually in their distribution for this DARPA Cyber Grand Challenge finals, they actually used this particular fuzzer for finding the vulnerabilities because it was much more effective. So this was really only changing in this one particular function of AFL. This is the key. Everything else was kept unaffected, just to make it clear. Everything was unaffected. We only changed how much time you spend in a neighborhood while doing the search. And this is done based on which paths you have explored earlier. You keep a memory of that. So you, in some sense, you make the search more intelligent. So I'll move on now to the fixing part, the patching part. Where, as I mentioned earlier, the DARPA Cyber Grand Challenge involved both the detecting and the fixing of vulnerabilities. So the work we are doing on fixing, I'll mention that briefly. So maybe let me play another video.
Heartbleed is a security vulnerability that affected 17% of secure internet web servers. It allows attackers to steal valuable data through insecure internet communication. The vulnerability is caused by a bug in OpenSSL cryptography library, and our tool, Angelix, can fix this bug automatically. Angelix uses program analysis and constraint solving to answer three questions. First, where to fix, that is to localize the problem. Second, what to fix, that is to understand the problem. And finally, how to fix, that is to solve the problem. Then it applies the synthesized patch to the buggy library implementation. The vulnerability is now patched. If the attacker attempts to steal the data, he will fail.
So I'll briefly mention this, the work that we are doing in auto patching. So just to give the problem definition for auto patching, here you have a buggy program as well as failing and passing tests. So the correctness criteria is given by tests, and the patching tool will produce the patched program so that at least it passes all of the tests that were provided. There are different ways of partitioning this problem into smaller sub-problems, each of which would be a search problem. So this is certainly one way, where to fix, as was mentioned in the video, so which line to fix. Then you decide what values should be returned by these lines, specifically for the test cases that you have. And then you want to essentially know what are the expressions that would return these values. So you can convert this problem into a function synthesis problem, synthesizing a number of mathematical functions, provided you are given this test data. Okay? So this would be one way of solving the problem. There are also other ways of solving the problem. Here is an example. This is a simple enough example so that we can see what is going on. Suppose this is only one line that is modified, and in this particular line, instead of bias equal to downsep, it should be bias equal to upsep plus 100. And you have all of these test data, and your goal is to modify the program so that it passes the test data. And oftentimes, of course, there would be a trivial way to modify the program, given each of these tests. Test input produce the test output, but of course you want to produce the minimal modification, because this is something the developer can accept. What is the minimal modification of the program so that it passes the test data? So the viewpoint that we take once you have decided where to fix, which is actually done by a fault localization step, is to generate this repair constraint. So given one particular test case, given any say failing test case, we would do a concrete execution up to that point, And at that point of time, we say, okay, say the right hand side, this is unknown. This is a function of all the live variables, all the variables that are live at this point, and we have to generate an expression in terms of these variables. Okay. So, you could call it bias equal to x, and then at that point of time you could do symbolic execution on x and thereby generate constraints on x, but whatever you generate on x, that is actually not x but a function of the live variables. So, you are getting some constraints on the function f that you have to synthesize. So, really the task becomes one of conjuring up a function, and so you have to solve constraints like this. Give me a function f which when given these inputs would produce a value greater than 110, and so on and so forth. And instead of solving this, instead of giving this to a solver and solving this, which would not be possible, as you might imagine, in general. So, you could either use program synthesis, which is what we did. So, you decide the primitive components like the operators plus, minus and so on that would appear inside each of these expressions, or you could even solve it by search. So, exactly I am not necessarily saying that program synthesis must be used, I am just saying how the problem of program repair can be decomposed, so that you can see this as a task of conjuring up a mathematical function. In fact, we found that the repair constraint could also be solved by search, because you could enumerate expressions over a given set of operators, and then you could enforce the axioms of the operators. Okay? And of course, in the degenerate case where you are just synthesizing a constant, you can use an SMT solver. Okay, we also released our tool. So, this is actually on this we have done a number of follow-up works. I only mentioned the very key idea in the very first work. We released our patching tool. In the initial version it was called SemFix, because fixing based on semantics, and the latest version is called Angelix. You can get this from this website angelix.io, and we have a growing community looking into this, and in fact next week I am moving on to Darkstool for this Darkstool on program repair. Okay, there is this overfitting problem in program repair, which all of these tools have to grapple with. So, here is a very simple example. Suppose if you can always have a trivial patch, suppose this is an error, you can always have a trivial patch if you just decide to remove this exit -2. Okay. So, there is in general this overfitting problem in program repair, because you are only generating a patch code which passes the test data. So, this is one key issue which all of these techniques are trying to solve. One area that we looked into is this anti-patterns, where you try to describe some constraints which should not be satisfied by the patch code that you generate, and you put that into the repair problem. And in fact, this is something we just presented in the FSC conference this year. So, I mentioned this overfitting problem because that allows us to compare it with some of the other approaches. This is our semantic approach, and as you can see, because this symbolic execution there is very controlled, it scales very well. These are really very large programs which are being repaired. This is a purely search based approach, but not doing genetic algorithms. It is using a customized search from MIT, and this is the GenProg tool, which is from Virginia, Michigan and CMU, several people involved, which is actually using genetic programming. So, earlier on it was established that this customized search based tool deletes much less functionality than the GenProg tool. So, what we did, we compared ourselves only with this customized search based tool and checked out that we are actually deleting much lesser, and this is not surprising, because the approach, since the approach is semantic, therefore, if it fixes inputs going through one particular path, it would typically fix all inputs that go through that path. So, this was in some sense the key intuition, that we essentially conjure up a mathematical function and generate fixes. This is the result that I had promised earlier in the video from the Heartbleed, where essentially this is the buggy program where there is no check on the payload. This is the fix that was generated automatically, and this is the developer fix. So 1 plus 2 plus 16 is 19, assuming I have my arithmetic right. So this is doing payload plus 19. If it is greater than this, then it is returning. And you can see that what the automatically generated fix is actually producing not something identical but equivalent. So if payload plus 18 is less, then it is continuing essentially. Okay. Okay, so that's all I have for the technical part. So this was some of the results on the binary analysis and vulnerability detection. It was done in the context of this project from the National Research Foundation on building trustworthy systems from COTS components. So how to take COTS components, which you can just get off the internet, and try to make it less vulnerable. We also looked into a number of other approaches, like how to cluster failing tests and so on, which I didn't talk about. The application of all of this is in software acquisition, because in fact we worked quite a bit with the government agencies in Singapore, because they would acquire software, or even when certain things are developed in-house, parts of the software may be acquired. So therefore they would like techniques to make the software more resilient. We are also working with developers with third-party code. They are interested in this. We are working with a particular company who are interested in using this technology for extending to binary analysis, and this is also useful for COTS system assembly. In terms of the conceptual contribution, one thing that I can mention is that symbolic analysis has been used a lot for guiding search in a very large search space. But one of the uses of symbolic analysis that we are doing in this work is to extract semantics. If you have a buggy program and you have no notion of the intended behavior is only given by test cases, how you can extract some semantics from there so that you know what is the function that you have to synthesize to make the program right. So really speaking, we are not using the symbolic analysis always for guiding the search. I have some material on the Singapore Cybersecurity Consortium that you mentioned earlier, but maybe this might be a good time to stop and take some questions here.